Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on amplifier. For this video, I'm going to explain as well as to compare the different classes of large signal amplifier. For example, we know that we have different classes of amplifier. In short, we have Class A, Class B, Class AB, Class C, and last but not least, Class D amplifier. This video, I'm going to explain the key feature and I'm also do a quick comparison between the different classes of amplifier. This will be the Part 9 series discussion on amplifier. So if you're keen to know more about amplifier, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on amplifier. This is my email. If you have any question regards on this discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and also the subscribe button. Please also turn on your notification bell in order to receive more information from this channel. Guys, once again, thank you so much for your strong support. This will be the flow of this video. Firstly, I will explain and also going to do a very quick comparison between the different classes of amplifier. I will start off by discussing the Class A amplifier, followed by Class B, and why we need to have Class AB in order to resolve the crossover issue of Class B, and then followed by Class C amplifier, and last but not least, a quick conclusion based on Class D amplifier. Before I start on the different classes of amplifier, let me define what is actually an amplifier. Why we need an amplifier? What is the role of an amplifier? In short, amplifier actually sit in between the input and also the output. From here, you can see that the input signal is fed to the input of the amplifier. At the output, we actually has an output signal. What is the key difference between these two signals? Input signal over here on the left and output signal on your right. You can clearly distinguish that the amplitude of the input and output is actually different. And output actually has a stronger amplitude as compared to the input signal, while the frequency remains intact. So basically, this will be the objective of amplifier. It actually boosts up the amplitude of the signal, while the frequency remains intact. Next, how can we actually quantify an amplifier? Okay, we typically quantify an amplifier based on efficiency. Okay, efficiency is basically a simple formula to calculate how efficient the amplifier actually convert the input signal to an output signal. And in general, is governed by this equation, POUT over Pin. POUT, which is the power at the output, and Pin is the power at the input. What we know when we actually learn in our secondary school day, when power or energy source is converted to another form, we actually have some loss. For example, we can have energy conversion loss to heat, to sound, etc. But for amplifier, it typically dominates by heat. Okay, when we actually convert from the input signal to an output signal, a lot of power actually lost to heat. And in order to quantify the amount of heat loss, we can easily compute by having the power at the input minus power at the output. This actually represents the energy loss, and hence, as I mentioned earlier on, the amplifier typically dominate by heat loss. So from here, I have some idea how much loss is due to heat by the equation over here. So over here, you can clearly see that in order to have a high efficient, which means that we are going to have lesser heat loss. When we have lesser heat loss, which means that most of the input signal has a better efficient to convert to the output. Hence, this will be desired. In short, to reduce or to improve the efficiency, okay, simply means that how to prevent any heat loss. Next, let's quickly discuss on efficient. Okay, so most of the amplifier in short here require a power source. DC power typically is used to supply to an amplifier. So in order to compute the power of the amplifier at the input, for example, okay, typically we have a input voltage source. We also have the DC power source. So as we know that power is actually equals to V over I. So from here, I will be able to calculate the DC power source that is actually applied to an amplifier. This is what I have introduced early on based on efficient. Basically, efficient is basically multiplied by 100. Okay, earlier on, I have mentioned this in order to know how efficient is basically the power at the output over the power at the input. And in order to convert into percentage, we multiply by 100. So therefore, we know how efficient the amplifier will be. As for class A, typically they has the least efficient. Okay, the maximum efficient for class A is maybe around 25 or maybe slightly better. Okay, but this is around the region of the class A efficiency. So because of the low efficiency, typically class A is usually not used when we actually require a very high power or watts of power are required. Then typically we will not use class A amplifier. So this video later on, you will be able to know which class of amplifier you actually need in order to amplify watts of power. Next, okay, this diagram here, I'm going to show you the IC, okay, the current at the collector versus the time for the different classes of amplifier. Let's take a look over here. Okay, so for class A, okay, you can see that they actually conduct all the cycles. So basically, this is for class A. Okay, as for class B, okay, typically they conduct about 50% or slightly less than 50%. As for class C, okay, is conduct even lesser than 50%. Okay, so class C, okay, most of the time is actually not conducted. As for class D, they actually use this PWM, pulse width modulation. Okay, so later on, I'm going to explain on this class D amplifier. But over here, you actually get a quick idea, okay, the different current at the collector versus the time for class A, class B, class C, and class D. Basically, you can see that whether they conduct 360 degrees or less than 50%, or even much, much lesser than 50%, or another form which is class D by using pulse width modulation. Let's do a very quick quiz. Okay, for example, okay, if I have a POUT which is 100 watt and actually my input is 200 watt, okay, you realize that I actually lost half the power. Okay, at the input I actually have 200 watt, and at the output I only achieve 100 watt, so I actually lost 100 watt. So hence the efficiency is actually 50%. Next, the efficiency of an ideal amplifier. Okay, if let's say it's an ideal amplifier, I'm pretty sure that in order to achieve ideal, okay, the efficiency should be 100%. Next, when efficiency is poor, okay, too much of the input power is actually converted to heat. Can you still remember? Okay, as I told you that for amplifier is basically dominated by heat. Okay, so any form of loss from the input with respect to the output, okay, is basically dominated by heat. Next, an amplifier that conducted for the entire cycle. Okay, remember, as I mentioned just on the previous slide, okay, for the entire cycle will be class A. Okay, next, an amplifier that conducted for about half. Okay, for about half is typically for class B. Okay, remember class B is about 50% or slightly less than 50%. Okay, so basically this is a very simple form of quiz in order to check whether you understand the different classes of amplifier. Okay, next, okay, a large signal amplifier can also be called a power amplifier. Okay, which means that for any large signal that we want to do it, we can actually use this power amplifier. Okay, this class A amplifier has a large quiescent collector current. Okay, so probably I cannot pronounce this word correctly. Okay, I would like to apologize if I didn't pronounce this correctly. So in short, okay, what are the things that we can actually compute here? So firstly, okay, we can compute the current at the base, okay, which is at the base here. So I actually apply a Kirchhoff voltage law. So for this part here, for DC, this actually shorted. So I actually apply a Kirchhoff voltage law, and in order to find the current that flow into the base of the transistor, I actually use this VCC divided by the resistor value, which is 1.2 kilo ohm. So from here, I actually compute that the current that flow at the base of the transistor is 15 milliampere. Next, I can also calculate the current at the collector, which is governed by this equation. This is basically the current gain of the transistor. So from here, I can compute that IC, the current at the collector is equals to 0.9 ampere. Okay, next, okay, I can also compute my VCE. VCE is basically the voltage in between the collector and the voltage. Again, over here, if I apply my voltage law, my Kirchhoff voltage law, I can actually find, okay, my VCE. Okay, so I spot a mistake. Okay, so sorry, this is supposed to be ohm, 12 ohm. Okay, so basically VCC, okay, minus the current of the collector multiplied by my RL, this will give me the voltage VCE, which is 7.2 volt. Okay, so once we have all this, we are ready to draw the characteristics of a Class A amplifier. Okay, for example, for Class A amplifier, the Q point, okay, so far is always at the middle. How I know the Q point? Okay, for example, earlier on, I have computed that my VCE is actually 7.2 volt. Can you still remember? And my IC is actually around 0.9. You can see here 0.8, 0.91. So basically 0.9 is in between 0.8 and 1. And my VCE is actually 7.2. So basically this is my Q point. So as I mentioned earlier on, the Q point of a Class A amplifier typically work at the center region here. So from here, you can see that I'm also able to calculate the power at the collector side. Okay, basically will be equals to 6.48 watt. Okay, next, let me move on to Class B. Okay, so for Class B, okay, it's slightly different. Okay, we are going to have this quiescent power dissipation, which is equal to 0. Okay, basically this is the Q point for Class B amplifier. Okay, which means that they actually don't have any power at this particular Q point here. Okay, so this will be the characteristics of a Class B amplifier. Okay, so again, let's take a close look on this Class B amplifier. Okay, so basically you can see over here, this is the performance of the Class B amplifier, the input signal. And at the output, okay, you can see that the collector signal is basically distorted, and hence it will be very bad for linear application, okay, because I'm not able to recover the original signal, which is a sine wave at the input, and at the output is basically just one part of the sine wave. Okay, so hence because of this, the signal actually distorted, and basically it failed to obey the linear application. So how can we actually resolve this? Okay, we can actually resolve this issue by having a push-pull amplifier. A push-pull amplifier will be able to resolve this issue. So how does a push-pull amplifier work? So over here, you can see that at the positive, okay, at the input here, basically the MPN will turn on, and basically they will supply this at the output of the transistor. As for the negative cycle, okay, the PMP will turn on, and basically they will supply the negative half of the cycle at the output. So basically this is how a push-pull amplifier actually works. Next, okay, again, let's focus on Class B amplifier. As I mentioned earlier on, okay, this is basically the input signal. Okay, basically at the positive cycle, basically will be so-called controlled by this MPN transistor, as I have illustrated on the previous slides. So once they go to the negative half, it will be used by PMP. And finally, at the output, okay, you can see that, okay, I actually have the linearity. Basically, the input and the output, they look like quite similar. So basically, this is actually desired for Class B amplifier. However, for Class B amplifier, if you look over here, okay, basically I need to have a 0.7 volt in order to turn on the transistor. Okay, so this become an issue. Okay, because the base emitter junction potential is 0.7 volt, okay, therefore I may have some crossover distortion. What happened here is basically when the input is in between 0 to 0.7, okay, basically the transistor will not be able to turn on. And because of this effect, I probably will not have anything at the output. Okay, anything that required to be at the output must be larger than 0.7. Then therefore VBE, okay, which means that the transistor will be closed. And hence, because of this, I will have crossover distortion at both the MPN and also PMP. And this is basically what we call as a crossover distortion. How can we actually resolve this crossover distortion? We'll be using this class AB. Okay, for this class AB, you can see that basically we design this resistor in order to have a 0.7 volt on the VBE, which means that this transistor is always on. Okay, basically it will be on. Okay, if let's say from 0 to 0.7, okay, I don't need the signal to be more than 0 or 0.7. It will be on. And because of this, I actually will be able to resolve the crossover issue. And as you can see from here, at the input here, the MPN will be turned on, okay, because it actually self-bias, okay, because I actually have a forward bias to the transistor. Okay, you can see over here, I actually has a voltage of 1.4. So which means that the transistor is actually on, and because of this, hence I will not have any crossover effect for the class AB amplifier. Okay, so next, okay, so this, okay, the quasi power dissipation in moderate for class AB. Okay, basically the efficient is much better than class A. Okay, so we can see that for class B is actually at 0. Okay, but for class AB is slightly better as compare. Okay, so over here you can see that the efficiency is definitely better than class A. Okay, so basically this is the reason, okay, why we need to have class AB amplifier. Okay, so a bridge tie load, okay, basically they will provide 4 times the output power for a given supply voltage and load resistance. Okay, so what does this mean? Okay, so basically from here you can see that this is actually a single end amplifier. Okay, you can see it's a push-pull amplifier here. So I actually have this, okay, so-called this cap require is basically to bias this here. Okay, no worry. Okay, you can see that this is actually at the output is actually VCC over 2. Okay, so for example, if I have my bridge tie here, you can see that basically it will be 4 times. Okay, because the voltage at the collector is actually equals to 2 times VCC. While over here you can see that VC is actually VCC divided by 2. So hence the voltage difference between these two is actually 4 times. So basically this is what it means. It can actually provide 4 times the output power for a given supply voltage and load resistor by having this bridge amplifier. Let's do a very quick quiz. Okay, so let's do a quiz to understand class A, class B, and also class AB. Okay, class A amplifier are biased to operate near where of the load line. Okay, so remember it's right at the middle of the load line or at the center of the load line. Okay, for class B, they basically have their Q point at the cutoff. Okay, so for class B, okay, basically they actually has a Q point at the cutoff. As for the conduction angle for class B, okay, how much will be the conduction for class B? Okay, is basically 180 degree. Okay, remember half the time it will not be on. Only about half the time is actually on. Okay, in fact, slightly less than 180 degree if we consider the crossover effect. To reduce distortion, okay, 2 class B transistors are arranged, okay, in a push-pull. Okay, earlier on, as I told you that without any push-pull, okay, only half will be turned on. Okay, remember what I have done earlier on the first part on the class B amplifier. By having just one transistor, basically I will only have the positive or I have the negative. So hence, because of this, the conduction angle is probably around 180 degrees. And in order to resolve this, I actually can have a so-called push-pull amplifier. Once I have push-pull, remember my NPN will take care of the positive cycle, my PNP transistor will take care of the negative cycle. Hence, I will have a conduction angle close to 360 degrees, which resolve the issue of Class B amplifier. Okay, basically for Class AB, okay, basically is a solution for a crossover distortion. Remember, for push-pull amplifier, we still need a 0.7 volt to turn on the transistor. And basically by designing a Class AB, okay, which means that the transistor actually has a self-bias, which means that we design to have a voltage of 0.7, okay, to turn on the transistor. Hence, when the transistor is at 0 or 0.7 volt, it still can be so-called turned on. Okay, hopefully you have a better idea on the Class A, B, and also AB amplifier. Now let's quickly understand the Class C amplifier. Okay, the class of an amplifier is basically determined by the bias point, okay, which establish the Q point. As I mentioned earlier on, the Class A typically they will be at the center. Okay, as for AB, okay, they will be very close to B. The B will be at the cutoff zone. Class AB is slightly above the cutoff zone. As for Class C, they basically established by reverse bias the base emitter junction, okay, which we are going to take a look on this Class C amplifier. Okay, so the theoretically maximum efficient for Class A, B, and AB and C, okay, you can see that basically for Class A, they operate 360 degrees. As for Class B, they typically work at 180 degrees. And in order to have them work at 360 degrees, we probably need a so-called push-pull amplifier. We also have this Class AB amplifier, okay, which is to resolve the crossover issue of Class B. And then next, we have this Class C amplifier, okay, which actually work 90% of the conduction angle. Okay, over here will be the linearity. Okay, you can see that the linearity for Class A is about 50%. Class B is basically 78.5. Class AB is in between A and B. Okay, Class C, they are 100%, which means that the input and output, they are actually identical in terms of shape, minus away the amplitude. Okay, for Class A amplifier, they are seldom driven to maximum output and typically they provide much less efficient. So from here, you can see that basically Class A, they don't have the efficiency, okay, but they have the linearity. As for Class C, they don't have the linearity, okay, but they have the efficient. Okay, so basically this sum out the different Class A, B, AB, and also C. Okay, so for Class C amplifier, okay, we actually utilize this 10 circuit. I have actually done this so-called discussion on Class C amplifier. So again, if you're keen to know more about Class C amplifier, take a look on the playlist under the description. Okay, over there, you will be able to find a series of discussion on Class C amplifier. Okay, basically for Class C amplifier will be by a reverse bias the emitter, base emitter junction. Okay, the transistor is off for most of the input cycle, and therefore the conduction angle is very small. Okay, so let's see how does the Class C amplifier waveform actually work, okay, with the 10 circuit. Okay, so over here you can see that this is basically a VBE. Okay, so at the collector, the current at the collector, which I had shown it to you earlier on. So over here you can see that, okay, when we actually have this low VCE, okay, when IC is flowing, you can see that when IC is flowing, we actually has a low VCE. Okay, in terms of how this exactly work, again, is at the playlist under the description. You can take a look on the Class C amplifier to understand this completely. But over here, you can see that when I actually has a current flow at the collector, okay, I actually has the lowest VCE. Okay, so basically, again, this is basically with signal biasing for this here. Okay, so over here, the base emitter junction actually rectified the input signal and charge this CC. Okay, so because of time constraint, I probably cannot describe the Class C amplifier again. Okay, again, please see the video. Okay, so when the signal bias actually increase, okay, when the input signal increase in amplitude. Okay, so basically these are the three transistor operating mode. Okay, firstly we have the cutoff. When we actually have the cutoff, it's actually like a open circuit. Okay, so we work in a linearity, which means that the input and output, okay, is basically linear. Okay, so which is predictable. Okay, once I become a saturation, okay, this become a short circuit. Okay, when they actually saturation. Okay, so the power at the collector will become zero when either they are at cutoff or when they actually at saturation. So in short, we actually want to ensure that our transistor work in a linear region. Okay, a switch mode amplifier actually use a rectangular input signal to drive the transistor rapidly between cutoff and saturation. Okay, which means that this switch mode amplifier actually switch the transistor very quickly between cutoff and saturation. Okay, remember, okay, earlier on I have shown you this. Basically, cutoff will be open circuit. Okay, for saturation will be short circuit. So for this case here, okay, for this particular case for switch mode, they actually want to switch very quickly between cutoff and saturation. And because of this, because we do open circuit, short circuit, okay, the efficiency hence will be very, very high. So this is actually a class D amplifier. Okay, so this is basically at the input. Okay, you can see that this is a pulse width modulation. Basically, is to switch very quickly from cut off to saturation. Okay, so basically, as I've told you that this will be a class D amplifier. Okay, if the switching frequency is good, okay, basically higher than the signal frequency, a class D amplifier is capable of linear amplification. Okay, in order to achieve linear amplification, okay, so therefore the switching frequency, okay, they must be higher than the signal frequency. If not, I will not be able to have the desired effect of a linear application. Okay, this pulse width modulation, okay, they actually work with a low pass filter. Okay, so basically you can see that this is basically a pulse width modulation here. This is an input signal. So how they actually work is basically this pulse width modulation. Okay, basically early on I actually has an input signal of a sine wave. They basically fit into the pulse width modulation. So at the output of the pulse width modulation, they have like a so-called a rectangular shape here. So basically in short, they switch very quickly from cutoff to saturation. After that, they pass through this low pass filter. Okay, the low pass filter actually reject all this switching frequency, and hence at the output, okay, will be an amplified sine wave, as you can see from here. You can see that in terms of amplification, okay, it is actually quite ideal. Okay, let's do a very quick quiz based on Class C and Class D amplifier. Okay, Class C amplifier actually use what circuit to restore the sine signal? Okay, so what kind of, they actually use this 10 circuit. Can you still remember? Okay, this Class C amplifier use this 10 circuit in order to restore the sine wave. The base emitter junction in a Class C amplifier is reverse bias. Okay, so if you still remember what I have discussed earlier on, for Class C, they actually has this base emitter work in a reverse bias in order to achieve this Class C amplifier. Okay, the theoretical maximum efficient for Class C is 100%. Okay, which means that this is the most efficient Class C, okay, for Class C here. Class D amplifier are also known as a switch mode. Okay, remember I told you that they are actually like a PWM, pulse width modulation. So they also know as switch mode is because they switch very quickly from cut off to saturation. Okay, and then last but not least, Class D amplifier, actually they employ a very duty cycle which known as pulse width modulation. Okay, so with this, I'd like to end my discussion. Please help to like and subscribe. Once again, thank you so much for your strong support. I hope to see you guys soon. Bye for now. Thank you so much.